All right. Good morning. So this is our last week where we're going to discuss new topics. I want to discuss some tests throughout this week regarding convergence of series, initially of a numerical series, but if time permits, we're going to discuss some functional series business as well. Next week, we have 2 classes. I'm going to reserve those for reviews. And even in this week, we're going to do some review. And you might have observed this. I've sort of toned down the tempo of the class a little bit. Because as far as I'm concerned, I was able to cover the main things that I wanted to cover, namely fundamental theorems of calculus and Taylor approximation. Of course, this is just the beginning, but in my experience at this stage, sort of fatigue sort of sits in, and like it becomes harder and harder to start new things. But maybe if I ever teach this class, next time I teach it, we'll just focus on analytic functions and just like get rid of complications of Riemann integrability or whatever. Because in principle, you see, I could just bypass any integration theory beyond Bourbaki, and Bourbaki integration theory is rather sort of simplistic, so that would help me create a lot of time to discuss other things. But anyway, so I should mention I'm kind of behind in the grading, so I still need to grade problem sets 8 to 10. 10, I should, according to regular schedule, I should release the grades of it release this Friday. So by the end of this week I'm going to release the other 2 as well. I apologize for being behind. Although perhaps what's going to happen is that I'm going to prioritize writing the solutions and doing the grading, and maybe the video for last week is going to come a little later. So that's that. Okay. So we were talking about the convergence of essentially numerical series, and also we were also sort of seeing in the horizon convergence of functional series. I still want to stick to the numerical series, develop some more tests that we can use to distinguish which series converges and which does not. So let's do this. Okay. One of the latest last statements that we proved last time was that if I was taking a formal series of numbers that converges, then the sequence of terms has to converge to 0. That is to say, if your infinite sum converges, then each additional term that you're adding, which ultimately, you see, this is ultimately the limit of the sequence of partial sums. So at each step, you should be adding less and less terms. And we formalize it by this. If this converges, then in fact, X bullets, the sequence of terms converge also, and it has to converge to 0. Then 0. Okay. Of course, this doesn't work the other way around. Just because a sequence converges to 0, it doesn't mean that the infinite sum converges. What is an example for that? 1 over n, exactly. So the harmonic series, for instance, if I were to plug in x sub n equals 1 over n, it certainly goes to 0, but the infinite sum, which is zeta of 1, blows up. It doesn't converge. Okay, this is very important. Okay. Now, I want to introduce perhaps a generalization of the same idea. And in fact, what I can say is this. I think I'm going to leave this as an exercise. So let this be a formal series, if it converges, then I can look at the tail sums. I'm going to write out what that means. The tail sums has to go to 0 also. If this converges, then limit as n goes to infinity of the sum starting from n. This goes to 0. Okay? So again, this is yet another formalization of the idea that if this infinite sum stabilizes at some specific value, that's what it means for this formal sum to converge, well, the tails, right? So if I were to get rid of the first capital N many terms and look at how much my partial sum changes after that capital N, well, that should eventually go to 0. Okay? And in fact, maybe, well, OK, I'll leave this as an exercise. The main idea is this, OK? So this is nothing but the infinite sum, the limit, minus the n minus first term. That's the idea. So n from 0 to capital N minus 1 x sub n. Right? This tail sum is the total sum minus the sum of the first n minus 1 or n terms. Well, if this formal sum converges, so the definition of that, so what that means literally is that this converges to this as capital N goes to 0, goes to infinity, which means that the discrepancy has to go to 0. Okay. I'll leave it to you to formalize the ideas here. I don't want to say anything further. What I would rather be able to do is to say, in fact, this is an if and only if. I would like to be able to go backwards as well. Okay. But now, if you think about it, we have some sort of an issue here. Because if I'm assuming that this tail series converges to 0, well, first of all, I need to make sense of it. And so the only reasonable way to make sense of this, or at least for our purposes, is this minus this, which means this is perfectly fine because it's a finite sum. But what is this? In order for this to make sense, I need to assume that this infinite series already converges. So you see, there is a definitional issue in turning this the other way around. And so one remedy for this is instead of looking at infinitary tails, I can just look at finitary tails. And I'm going to come up with what is called the tail criterion. Okay? You could also see the word Cauchy criterion for series. So tail test, aka Cauchy criterion for series. Says this. Let's let sum of xn be a formal series. Then the tail test gives an equivalence for this formal series to be convergent. It says this. Then this converges if and only if. Now I'm going to write down an epsilon delta statement, okay? Or epsilon n statement if you want. For any epsilon there is an n such that for any lowercase n after uppercase n, and for any p arbitrary, positive or non-negative, well, this finitary tail, where I'm adding all terms from n to n plus p, is within an epsilon of 0. Okay. Okay, so let's try to understand what is happening here. First of all, we have the word Cauchy. We've heard this name a couple of times. Cauchy was a mathematician who played a big role, in fact, in the rigorous treatment of calculus. And in fact, if you sort of look into the history of a class like this, you're going to see, like way back when, Cauchy was the main person who realized, oh, you know, there are a bunch of like pitfalls in this calculus business. And so when we're teaching it, we should be emphasizing rigor as well. And, you know, like he was French and he wrote this book. And then at the time, people could not understand what the point was. Like, why are you making a big deal out of all this and stuff? But of course, over time, you see, culture changes. Now, somehow, the format of this statement has to do with a general Cauchy property, okay? When we were first talking about the convergence of a sequence, for instance, I also mentioned there's also something called a Cauchy sequence. And for real numbers, Cauchy is the same thing as convergent, okay? Now, I want to take my time and go through some of these ideas around the Cauchy property. I'm going to write sort of different incarnations or reincarnations of the same idea. For instance, some of them in terms of like Riemann sums, whatever, too. Okay. Let's see. So before I do that, though, I want to justify why this is an important thing. And here's the mother of all convergence tests for series, okay? This is one of the most important one of the most important tests. And it is called the comparison test. Let's first assume the tail test for a while. Assuming this, we're going to prove the comparison test, look at some examples as to how it is useful, and then we're going to go back and sort of study this Cauchy property. And that's going to be some sort of a review also. So maybe I should write proof in a bit. Because it's going to turn out, for instance, that once you write this properly, this tail test has very little to do with infinite series. All it has to do with it is that these terms are real numbers. So somehow, ultimately, this Cauchy property ends up being equivalent to the completeness axiom of reals, all the way down in week 1. Okay? We'll see all that in a second. First, I want to take this for granted and establish this comparison test. Comparison test. Okay. Let me be clear here. Okay. I'm taking two sequences, X bullet and B bullet. I want B bullet to be taking non-negative values, be two sequences. Okay? I want to say something like this. If the formal sum of B bullet converges, and if B bullet dominates X bullet, then X bullet should converge also. Okay? here. If this converges and I want to say that the terms coming from the B bullet sequence dominates eventually, at the very least, the terms coming from X bullet. Well, I can just say X sub n is big O of B sub n as n goes to infinity. These are my two assumptions. Then, in fact, I can say that the infinite series made up of X bullet also converges, and I have a bunch of statements. Maybe I should say ABC here. These two, then this infinite sum also converges. In fact, by the definition of big O, it converges absolutely. That is to say, the infinite sum of absolute values of X sub n converges. And we have this nice domination property. Okay. Before looking into the proof of this, let me give a couple examples. So you see, generally speaking, even though there are certain situations where you don't need to do calculations like we were doing last week, the better form of arguing, typically in this business, is to use some sort of a comparison test. So the two series that you should compare to are geometric type series, powers of some number added up, or some sort of a zeta type function, or harmonic series type of a thing. You can also look at the contrapositive of this, and you can say, for instance, if this guy diverges, then anything that dominates it has to diverge also and stuff like that. But I'm not going to write that down. So let me just write one example or two examples here. This converges. Of course, it does so absolutely. Certainly, it should converge. It should converge to the E number. But maybe I should ask you, how can I perhaps argue, if I didn't know the definition of the number E, that this series converges? I want to keep calculations to a minimum. Think a little bit. So can I come up with some series, right? I want something like this, such that its terms dominate reciprocals of factorials, eventually at least. If I can come up with something like this, such that this converges, then I would be done. Well, the idea is this, okay? N factorial means 1 times 2 times 3 times 4 times all the way up to n. Well, if I were to just fix one positive integer larger than 1 and look at its powers, well, eventually n factorial has to exceed it, right? So for instance, I can say 2 to the n is big O of n factorial as n goes to infinity. If I want, I could have written 10 to the n, right? Because here too I'm multiplying n many terms, but at each time the factor increases. Here the factor at each time is the same. So eventually factorial is going to beat an exponential. That is to say, the reciprocal of this is going to be big O of the reciprocal of this. We know that the sum of this converges to a specific number, in fact, but we don't even need to know what that specific number is. Because this is the case, by comparison, we're done. Okay, so that's to converge. Make sense? What if I were to put here in the numerator log of n2? Log of n divided by n factorial. You see, I can just make these terms arbitrarily ugly so that you can't quite just explicitly compute things. But at the very least, you should be able to argue, oh, this converges to something. And then maybe I can ask my computer friends, whatever, to simulate or give me some estimate as to what the limit is. Okay? If I were to multiply this by log of n2, it's going to be the same. That's the point of big O. It's like log of n is not going to affect that much. You can just ignore that part. Anyway. So for instance, how about this? Example. Let me look at zeta of 1/2. So I'm looking at the sum of square roots of integers. Hang on a minute. Do you think we can? Let me think. Well, I would hope that this diverges. I mean, I know that it diverges, but let's see if we can use the comparison test to figure that out. Because I know at this point that zeta of 1 diverges. We know zeta of 1, which is the sum of the reciprocals, diverges. Oh, OK, that's good. Well, I know that this is the case, like this. Well, if that is the case, I have this. If this diverges, this has to diverge also. OK, there you go. Okay, so it's very useful, you see. It's like trying to compute more explicit estimates for this is going to be rather messy. So there are sort of like very important examples. For our purposes, geometric series and zeta type things are going to be the most important series that you're going to compare things to. Okay, any comments or questions? So, yeah.
I'm saying, like, why is it sufficient to just show that one of these, like, there's one sequence that dominates it?
Well, OK, yes, because suppose this converged, but then because this happens, I should be able to apply the comparison test and deduce that zeta of 1 converges also.
Right.
But I know that zeta of 1 does not converge. Yes. Say again?
So square root of n is here, and then you flip.
I sent this to this side, this to this side.
Oh.
Yeah, these are non-negative numbers, so there's no flip. Yes. If these were negative, then I would need to flip, but in this case, no. Yeah. Yeah, so just to reiterate, if you have a series that you know converges, then any other series that you know this series dominates has to converge as well. And vice versa, if you know that the series diverges, then any other series that dominates it has to diverge also. So, okay. Now, I want to prove comparison assuming tail. Then we're going to spend the rest of today on the tail test. Or rather, this Cauchy property, really. I'm going to go back to the world of metric spaces. And sort of we're going to pick up from there. So I want this to be some sort of a review also. So proof of comparison assuming tail. Oh, comparison. Oh. I'm assuming tail test. Well, I have two assumptions. I need to just open them up. I'm gonna open up assumption A using the Cauchy property here. And assumption B, I'm just going to open up the definition of big O. And I'll remind that too. By tail test, A gives that for any epsilon, there is an n, such that for any lowercase n after uppercase n, and for any p, this finitary tail of b sub n is bounded by epsilon. Okay, now let's open up the second hypothesis. What does this mean? It means that up to some constant, for lowercase n large enough, x sub n in absolute value is going to be bounded by b sub n. That's what big O means. Right, so there is some constant c and some capital, maybe I should use a different letter. Let's say n prime. It's not necessarily the same thing. Such that after this time, capital N prime, x sub n in absolute value is upper bounded by c times b sub n. That's the definition of big O as n goes to infinity. Okay. Well, if that is the case, if I were to look at the finitary tail of x sub n, I should again be able to get some sort of a bound, is the point. And for any lowercase n after max of n and n prime, so that I have both this property and this property, and for any p, this finitary tail in absolute value let me think. Now let's see. Triangular gives me that this is like so, which then I can replace this, c times this guy. Okay, and I know that this is upper bounded by c times its absolute value which I know is bounded by c times epsilon. Okay, I could have fudged around with the epsilon to be, whatever. Epsilon divided by c plus 1 if you wanted to get epsilon here. But in any event, I was able to show that the terms, the finitary tails of x sub n also satisfies this part of the tail test, which again by the tail test, therefore I can conclude that the infinite sum of x sub n converges. In fact, this also converges. Okay. I actually showed 1 and 2. I'll leave 3 to you. It's a nice sort of thing to think about. It's kind of implicit in what I wrote, but I proved 1 and 2, in fact. Okay. Pretty nice. Now, what I do want to do now is go back to the tail test and really understand what is really happening here. Specifically, I want to focus on this Cauchy property. Now, first of all, let's try to write it in a more, in a different format that is more amenable to what I want to go toward. This was, in fact, something that we've seen in a previous problem set as well. I would rather think of this finite sum as a discrete integral. Okay? I want to think of some sort of a cocycle property again, but for finitary integrals. Okay? Finite sums. Because you see, I have here 0, n, and n plus p. The thing that we're controlling over here, this, is the sum from here to there. By the cocycle property, the sum from here to there should be equal to the sum from here to there and from here to there. Okay? The sum from here to there should be minus the sum from here to there, which means this is just like a very long way to say that this is the difference of this minus this. Add up the first n plus p terms and subtract from it the first n terms. That is to say, this is the n plus pth term of my sequence of partial sums, and this is the nth term of the same sequence. Okay? And so what I'm really saying here is for any epsilon, and there is an n, such that after this n, if I were to compare two distinct times, the distance between them is within an epsilon. Okay. Any comments or questions about this so far? Now let me state Cauchy criterion for Riemann integrability. I'm going to leave this as an exercise. Or integrability. Let K be a compact interval and f be a function on K taking real values. then f is Riemann integrable. If and only if, I'm going to try to write something similar. This time, I'm going to compare the distances between two Riemann sums, okay? If and only if, you see, instead of choosing first a target integral value, because I'm not going to look into that, all I want to compare is two distinct Riemann sums that are both sufficiently fine. If for any epsilon, there is a delta, remember for Riemann integrability, we're just looking at constant gauges. For any, let's say, P1, S1, and P2, S2, two sample partitions. If both of these are delta fine, or yeah, delta fine, that is to say, if both of the meshes are bounded by delta, then the associated Riemann sums they differ only by an epsilon. Okay. I hope at the very least you're seeing some sort of a formal similarity between that Cauchy property and this Cauchy property. What is the difference? There, I'm just looking at the sequence, it being Cauchy. Here, I'm looking at a net, more complicated type of a sequence being Cauchy. I'm saying if I go far enough into the future, any two times, so the values at any two distinct times is going to be within an epsilon. Okay? Of course, I could have done the same thing with HK integrability. I would have said f is HK integrable. If for any epsilon there's a gauge, so I said for any two sample partitions, if both of them are delta fine, then the associated Riemann sums are within an epsilon. I'm not even going to write that down. I'm going to leave it to you to write it. Exercise. Same for HK integrability. Here's a next exercise. Here's a Cauchy criterion for uniform convergence of functions. Okay. Of sequences of functions. Say you have a sequence of functions on some set. Okay. Remember, on this set, I can talk about the C0 distance, if you want bounded. You see, if I want to talk about the uniform convergence of this, so far what we were doing is, oh, there is an f infinity, there is a target function. And then we were looking at the error to that target. But with Cauchy, you're getting rid of that target, you stop referring to that target, and you start talking about the error in terms of two different terms of your sequence, net, whatever. So I'm going to say this converges uniformly. If and only if, for any epsilon, there is an n, non-negative integer, such that for any lowercase n after it, and for any p, non-negative, the C0 distance between the nth term of my sequence and the n plus pth term is within an epsilon. Okay. let's do one final criterion, Cauchy criterion for sequences, for convergence of a sequence of numbers. Cauchy criterion for convergence of sequences of numbers, of real numbers. Let X bullet be a sequence taking real values. Then X bullet is convergent if and only if I'm going to try to write something similar. Again, I'm not going to say there's a target such that the discrepancy to that target is bounded. I'm going to compare two distinct terms of the sequence. If and only if for any epsilon positive, there is an n such that for any lowercase n after uppercase n, you get the point at this point, I hope. And for any p, x sub n minus x sub n plus p is within an epsilon. Okay. Now, at this point, I hope you would agree with me that if I verify this exercise, that immediately implies this. Because here, what I'm doing here is I'm just looking at s sub n minus s sub n plus p in absolute value. So if I start with a sequence, I can look at the sequence of partial sums. That itself is a sequence of real numbers. And I would, in order for that sequence of partial sums to be convergent, well, this has to hold. So this exercise immediately implies this. Okay. So throughout the textbook, you're going to see in different contexts, there's always at some point a Cauchy criterion stated this way. I sort of postponed it because we didn't exactly need to use it, but it does end up being useful in many contexts, especially when you have a sequence that you want to converge to something, but you don't quite know to where. You don't have quite an idea. You don't quite have a target in mind. Okay? In those kind of situations, it ends up being rather useful to, instead of comparing to some, inaccessible target that supposedly exists, the distances between any two terms after you wait finite time, after you wait some time. Okay? And I'll say this too, even though in these different contexts, so for instance here, I think in the textbook they call this sequence uniformly Cauchy, because Cauchy relative to the C0 metric, uniform metric and stuff. Okay? I'll say this too, in all of these contexts, even though things kind of look a little bit different, the only reason ultimately why all of these work is because you're taking values in the reals. Okay? So I should say of real numbers or real functions. Functions that take values in reals. Okay, we're going to discuss that part as well. Here too. Here, I'm trying to integrate a function that takes values in reals. Consequently, Riemann sums take values in the reals. Hk integrability is the same. Here, I'm taking a sequence of functions that take values in reals. And here too, my sequence is again taking values in the reals. I guess what I'm trying to say here is that now, perhaps when you switch over to multivariable calculus, you may want to start looking into series made up of terms, taking values in a more complicated space where addition is defined, whatever. Okay? Or maybe you want to talk about like vector-valued functions, all that stuff. Now things get a little bit more complicated, but we're not going to go there because we're just focusing on single variable calculus part. Okay? Any comments or questions about this so far? So what I want to do now is to transition to the general definition of the Cauchy property, say for sequences and for nets as well, so that you can talk about these Riemann nets or Darboux nets, whatever, or HK nets, all these things. Probably we're not going to have time to prove things, but at the very least, I'd rather define it. For X a metric space, because you see, even though all of these things work ultimately because things are happening in the reals, Cauchy property itself, at the very least, can be defined using metric spaces only. Even beyond, but we're not thinking about anything more abstract than metric spaces. Let X be a metric space. So for instance, it could be a subset of reals. It could be this set of bounded functions. It could be a set of continuous functions, whatever, differentiable functions, many things. And let me let X bullet to be a sequence. I'm going to call X bullet Cauchy if the appropriate property holds. Essentially this, except that I'm going to use the general metric space property, metric space notation. It's a Cauchy sequence, maybe I should say, is a Cauchy sequence F, okay, for any epsilon, there's a capital N, so I'm waiting finite time. And then after I wait finite time, I'm comparing two terms that are farther enough in the future. And then I look at their distances. I want this distance to be within an epsilon. Okay. I literally took this, and instead of writing the metric in the reals, I used the abstract metric space notation. Okay, it's the same thing. Okay. Next time, I want to state what it means for a net to be Cauchy as well, so that we can make sense of this as well in the HK. But we're going to go from there. We're going to understand how convergence relates to Cauchy. OK, thank you. All right, let's start. Good morning. I take attendance today. So today, we're going to do some sort of a review. Namely, we're going to focus on this Cauchy property. So this is, even though it's not exactly the context of continuity, it's very similar. The proper name for today's context is what is called uniformity. So uniform continuity, for instance, also belongs to the same context. We're going to discuss Cauchy property in different contexts, and we're going to ultimately do some of the exercises that I mentioned yesterday. This is so that we have this tail criterion for a series of numbers or functions. OK, so the standing exercise for today is, I don't know how far we'll be able to go, but I'm going to state certain theorems. And depending on how far we go, I'm not going to continue tomorrow, and I'm going to leave the completion of the proofs to you, because these are, as far as I'm concerned, not really within the realm of calculus. And those of you who are going to take more advanced classes, say in topology or whatever, or logic, descriptive set theory, these kind of things, you're going to sort of look at arguments like this anyway. And I hope you're going to see the sort of difference in the flavors of the arguments also. So we're not going to need to dirty our hands quite a bit for many of the arguments that's going to follow. OK. And most of the arguments I'm going to give for sequences, but I just wanted to remind you the notion of a net, what it means for a net to converge. I'm going to define a subnet. So far, I've been avoiding the notion of a subnet, even though we were using it underneath the hood. And then we're going to define a Cauchy net. And then we're going to go from there. But mostly, I'm going to leave the net versions of the statements to you also. OK, now remember that a directed set is a pair, A and this less than or equal to. This is supposed to be sort of some formalization of our notion of time. Namely, we need to have a certain direction toward the future, which says that it has to have two properties. So A is a set, and this less than or equal to, or this curly less than or equal to, is a relation on A, which, if you remember from week 1, means really this symbol stands for a certain subset of A times A. If you remember from week 1, that's what we defined the relation to be formally. But instead of course, writing alpha beta, this pair is in this relation, we write it like this to be faster about it. But formally speaking, we're still in the realm of week 1 when we're defining the notion of a relation or using. Well, one of them is that one of the properties this relation is supposed to have is that it's supposed to be transitive. So for instance, if beta is a time after time gamma, and if alpha is a time after time beta, then certainly it must be the case that alpha is a time after time gamma. OK? This is the first property, transitivity property. This was also included in the notion of an equivalence relationship. One of the axioms was this. So you see all of these properties have multi-uses, many uses. The other property is the filtering property. Namely, if I were to take two times, alpha 1 and alpha 2, I should be able to find some time in the future of both of these times. Okay? For any alpha 1 and alpha 2 in A, there is some beta such that beta is simultaneously after alpha 1 and alpha 2. Okay? And so I was thinking about sort of like how to visualize or imagine nets and stuff like that too. I'm sort of imagining, so I came up with two ideas. One of them is sort of imagine sort of like a pond, and you drop a little pebble, and then there's these wave fronts. Okay, that's one representation, I think, that is reasonable. Or if you imagine sort of like speaking, you know, your voice sort of like, again, sort of propagates in waves. That's sort of one version of an interpretation of what a directed set is, or equivalently a net too. But let's just stick to directed sets. Another one is a lightning, right? So it starts somewhere, you don't quite know, but then it sort of trickles down like this. So you have a direction toward the future. It's just that there are multiple branches happening. Okay? Anyway, certainly, for instance, non-negative integers, right? So the domain of a sequence is a directed set with the standard direction, so less than or equal to. But there are many other. A net in a set is nothing but a function from some directed set into X. So this is a generalization of a sequence. The point here is that sequences, the way we were discussing them, are nets. There are specific examples of nets. But so are, for instance, Riemann integrals. Okay? So once you pick a function, and if you think of the Riemann sum as something, as a function of the sampled partition, that's a net. And in terms of, so if you were to define this to be on S bar, into reals, let's say. This gives you the Riemann integral, the convergence or divergence of this. But if you were to define this on gauged partitions, that gives you HK integrals. Okay? So in a sense, we were using the notion of a net as well. And now you have the experience of using these different ideas. And you see in practice, they might look very different. But underneath the hood, people realized a long time ago that they really satisfy the same sort of general axioms. And just based on this, you can deduce certain things. Here's again part of the recap. Now, instead of just a set, if I were to assume that X is a metric space, now I can talk about convergence because I have a distance on X. And if I were to fix a target, X infinity, well, I'm going to say that X bullet, the net parameterized by A, converges to X infinity if the standard epsilon delta thing happens. Right? So for any epsilon, there's a time A, such that for any time after this capital A, the distance between the target and the alpha term is at most epsilon. And so this is formally, at the very least, the same as sequence convergence. Right? So in the case of sequences, we would, instead of having curly A, we would have non-negative integers. And we would say for any epsilon, there's an n in the in the integers, such that for any lowercase n, after this uppercase n, the same thing happens. See, it's pretty much the same. And as before, of course, this stands for the tail. OK. Now, I want to define the notion of a subnet. So far, I've been avoiding it because there are multiple, in principle, distinct definitions of a subnet. But I would want to say things like, oh, the Riemann sums that would give the HK integration, in fact, is a subnet of the Riemann sums that defines Riemann integration. And this is also the reason why, in general, it might happen that this converges, but not maybe this. That's why Riemann integrability implies HK, but not vice versa. Here I'm saying, oh, a subnet converges, but not maybe the original one. Anyway, so the complication here, essentially, because of the following, in the world of nets, you're not fixing the domain. So if you were to choose two different nets, in principle, their domains could be two distinct directed sets. You see? So here, A is one directed set, B is some other directed set. You have no idea, in principle, how these are related. But this is how we define it. This is one of the ways to define it, which is going to work in our results also. I'm going to call Y bullet a subnet of X bullet if any tail of X bullet contains some tail of Y bullet. So let me write it like this. If for any A in A, for any time according to A, there is a time according to B, such that, now I'm going to look at the tail of Y. This is a tail for a Y bullet. This, I want it to be included in the other tail. That should be capital B. Subsequences are subnets of sequences, so the definitions coincide. However, sequences might have subnets that fail to be subsequences, which is also one of the reasons why I avoided this subnet definition. It's kind of confusing. Let me define what it means for a net in a metric space to be Cauchy. Well, I'm just going to take the definition of the Cauchy property for sequences and adapt it much like the same way I did over here. Maybe I should add the definition of Cauchy property here too. For X, a metric space, and X bullet, a sequence. X bullet is Cauchy if for any epsilon, there is an n such that after it, if I were to choose two distinct times, or maybe the same times, then the distance between them is bounded by epsilon. Okay, so you just take this definition and adapt it to nets. Write it here. Let X be a metric space and X bullet be a net. I'm going to call it the Cauchy net. It's Cauchy. If for any epsilon there's a time A such that for any two times after I have that the distance between the associated terms is at most epsilon. Okay. Like I said, I'm not going to use the nets. I'm not going to discuss them that much further. It's going to be, again, a standing exercise to adapt these results to nets. We're just going to focus on sequences. Maybe I should add it here, perhaps. Yeah. Adapt all the statements that we're going to discuss today to nets. So that consequently you have the Cauchy criterion for Riemann integrability, Cauchy criterion for HK integrability. You have a bunch of different things downstream from this. OK. Before I go any further, I want to spend some time discussing the intuition behind this Cauchy property. OK. Now, remember the intuition behind convergence for a sequence. For convergence, what we had was this, right? So maybe I should write it like this. In order to talk about a convergent sequence, right, you need to have your terms. You need to have your dynamical object, positions that change in time, x bullet. But also, you need to have a target, x infinity. Need dynamical. Let me say time dependent. Time dependent. X bullet and time independent. X infinity. And so if this is my space X, I already need to, so initially I need to fix a target. This is going to be stationary. It's not going to move. What does move is this X bullet. X1 is here, say, and then X2 is here, and so on. And I'm imagining that these subscripts are my time parameters, and my time is discrete. And at each time step, it possibly moves to a different place. Maybe it stays at the same place. It could repeat. Okay, maybe it repeats like this. Maybe it goes back. But so this is, for instance, x4, x5 also, and then maybe at x times 6, it's here and whatever. And what was the intuition behind convergence? In order for x bullet to converge to x infinity, well, what must happen is I'm going to look at some epsilon ball centered at this target. And what should happen is, after finite time, my sequence should be trapped within this epsilon ball. So in this ball, after finite time, after finite time, that of course depends on what this epsilon is. If you shrink your epsilon, now your trap is more refined. Then quite possibly you're going to need to wait longer. But the point is, insofar as you can do this for any epsilon, that's what we mean by x bullet converges to x infinity. Okay? This is always the idea. This is the idea for convergence of a sequence of numbers, convergence of a sequence of functions uniformly, let's say. All that differs, all that changes is, for instance, if I'm thinking of x bullet as a sequence of functions, and if I want this convergence to be uniform, well, this distance is the uniform distance, supremum distance. But the general understanding is still the same. You see, this is rather nice if you already know a time-independent thing, if you already have a target. And so even in the syntax, we had some issues. For instance, if I say x bullet is a convergent sequence, I really mean there is some x infinity such that x bullet converges to x infinity. Okay? So in order for me to be able to say x bullet is convergent, I also need to refer to some target, even though in principle maybe I don't have access to it. And so Cauchy sequences somehow becomes more convenient when you don't quite have when you don't quite have access to this time-independent target. For Cauchy, all you need is a time-dependent thing. You're not deferring to any target whatsoever. Okay? So you don't have this absolute target relative to which you're going to measure your error. Okay? So the intuition for Cauchy property is this. I just have this time-dependent thing. And again, as time progresses, it moves possibly. Maybe it repeats a couple times. But ultimately, what this Cauchy property says is, again, some sort of a stabilization. In the case of convergence, I wanted to trap my sequence within this epsilon ball. In the case of Cauchy, since I'm not quite referring to this target, what I'm going to do is I'm going to compare the volatility. That is to say, I'm going to compare, say it moves like this. Where the sequence is at time n, and then where it is at time n plus 1, and at time n plus 2, and so on. What I want is that I would draw, so for Cauchy property, I demand that my sequence asymptotically moves less and less relative to its other terms. It changes less and less. Okay? So it's almost like this. Maybe I can draw it better. Say I start here, and it starts moving. Goes here. And then I wait finite time. And then after it, these balls I draw centered at the terms themselves. That's an epsilon ball. Okay? And then I want the consequent terms to be within this ball. Okay. Any questions about these two? Yeah.
So are all convergent sequences going to be Cauchy?
Yes.
But not. It doesn't go. Does it go the other way as well? Are they both-
Yes. Sometimes it does. Yes. For our purposes, it's going to go the other way around as well. Yes, very good point. So what your colleague is suggesting is, if you have a convergent sequence, it has to be Cauchy. By the way, you read it as Cauchy. That's how you read it. Cauchy. So if you have a sequence that is convergent, it has to be Cauchy, but not vice versa. And here's the reason. If you start with a convergent sequence, then after finite time, you're going to be within an epsilon. All of your terms after finite time is going to be within an epsilon. That means that if you compare two terms, okay, that are sufficiently further into the future, well, they cannot be more than 2 epsilon apart from each other. Okay? So this property is always going to imply this, but not necessarily vice versa. One of the reasons why reals work, and we were using real numbers, is that for real numbers, with the standard distance, it works the other way around too. Okay? And that's what we're going to discuss. Any other comments or questions? Okay. And so here's the first theorem. I'm going to have 2 theorems, okay? One of them is going to be about the relationship between convergence, Cauchy, and some other relationships. Okay, so some other properties like boundedness and stuff. The other one is going to be about a space having this nice property of Cauchy implies convergent, and function spaces using this set or space. So first theorem. Let X be a metric space, and X bullet be a sequence in X. Then we have this. If X bullet is convergent, it is also Cauchy. Second, if X bullet is Cauchy, it is bounded. Third, if X bullet is Cauchy, then it is convergent if and only if some subsequence of it converges. then it is convergent if and only if it has a convergent subsequence. Let's postpone the proof of this. And just by using that, oh, maybe I should define one final thing so that we have the proper terminology. I'm going to call the metric space complete if any Cauchy sequence converges in it. Is called, if you want to be more precise, this is called Cauchy completeness. In it is convergent. And based on this definition and the theorem, we can immediately write this corollary. Reals is complete. And so is any compact interval. What does the corollary say? It says that if you have a sequence of real numbers that is Cauchy, then the sequence has to converge. Just taking for granted this theorem for a second, let's think about how to argue for the corollary. So assuming the theorem, how to prove the corollary. Let's think about it a little bit. Instead of going into the proofs of the theorems and stuff, this is the most important thing for our purposes. Say you have these three statements. How can you argue? I'll give you a couple minutes. And here's the definition of what it means for a sequence to be Cauchy, what it means for a metric space to be complete. And the main thing you're going to use is this theorem. You can do proof by contradiction, but there's a much more straightforward direct proof.
Nipples on a Weierstrass?
Yes, but how? Tell me more. Tell me more about it.
Because in R you have that every sequence has a convergent subsequence for R and compact intervals. Then the backwards implication is true, so you have the corollary. Exactly. This is sure. It works for compact, but compact subset too, if you want. Let's first look at the real case. I have some Cauchy sequence in the reals. I want to use the theorem. Oh, is it because it's bounded?
Okay. So the theorem says, if I start with a Cauchy sequence, this sequence is automatically bounded. Now Bolzano-Weierstrass
allows me to extract a convergent subsequence, but then by item 3, I have a Cauchy sequence that has a convergent subsequence, which therefore has to be convergent. Okay? That's the proof. If I have a Cauchy sequence by item 2 in the theorem, it is bounded. By Bolzano-Weierstrass, therefore, X bullet has a convergent subsequence. Bolzano-Weierstrass, X bullet has a convergent subsequence. And again, by 3, X bullet is convergent. Therefore, any Cauchy sequence in the reals is convergent. That's what it means for reals to be complete in the sense of Cauchy. Make sense? This assuming the theorem, of course. We're going to get to that in a second. Now, I should mention this. The reason why I said Cauchy complete is because even though we use the phrase complete before, all the way back in week 2, I think, one of these axioms that reals has, I said, is the completeness axiom. It turns out that that notion of completeness is a slightly different notion of completeness, but due to magical reasons, in just this context, that is to say, Archimedean metric fields, Cauchy completeness ends up being equivalent to this other completeness. Okay? So, and in principle, we actually didn't need to discuss this other completeness axiom. We could have just taken the completeness to be this as well. This is like a funny factoid about the foundations of reals, whatever. Okay. So, let's see. I think I'm going to postpone the proof of this just a little bit more and state the other theorem that's going to be important for us. And this other theorem relates the completeness of a set to completeness of functions of sets. Set functions, rather. And it goes like this. Maybe I should call that theorem A, and this other one theorem B. Let Y be a metric space. Then the following are equivalent. That Y is complete as a metric space. Well, for any set S, I can consider the set of bounded functions from S to Y. That is a metric space with the C0 metric. That metric space is complete. Relative to the C0 metric. And for any metric space, the bounded continuous functions from X to Y is complete. That's also equivalent. Okay. which means pretty much any set of bounded functions taking real values is complete with respect to the uniform metric. So you can just take a Cauchy sequence of functions. Once you take a Cauchy sequence of bounded functions, that is automatically convergent. It has a limit. You may not be able to access it, but it has a limit. Okay? Or if I were to take an interval and look at the bounded continuous functions taking real values on it, that is already complete automatically based on this theorem. Okay? So you see, these kind of things end up being very useful when you're looking into infinite series of functions defined on the same thing. Because you know the terms. If you can figure out, well, the volatility of this series of partial sums is bounded asymptotically by an epsilon. That is to say, if this infinite series is Cauchy, then you're going to be able to say, oh, this infinite formal sum is in fact convergent to some function. It's a well-defined function, you're going to be able to say. OK. Maybe I should give a couple examples of metric spaces that are not complete. For instance, just so that we have an idea, rational numbers is not complete. Complete. Okay. How can I justify this? Maybe let's think a couple of minutes about this. How can I say that rationals with the standard distance is not a complete space? I need a Cauchy sequence made up of rational numbers that is not convergent. The point here, of course, is that when we're talking about convergence or divergence, I need to say, if I start with a Cauchy sequence of rationals, it converges to a rational number. Okay? So to justify that rationals is not complete, I should be able to come up with a sequence of rational numbers, okay, that converges to some irrational number. Okay? Well, I can come up with something like that by just, approximating decimal by decimal some irrational number. Right? I can take square root of 2. There are like multiple methods of like approximating using rationals. Just take one decimal at a time. Okay? Maybe I should write that a little bit. So consider the decimal expansion I should say one decimal expansion. There are multiple of root 2. Yeah, so I can come up with it. I can say, oh, root 2 is between 1 and 2. Therefore, root 2 should be of the form 1 dot something. And then I can just like keep looking at powers of 1 over 10 whatever, and keep sort of guessing further and further decimals this way. So there's an algorithm to do this. Because this is irrational, I know that the decimal expansion is never going to repeat. Because if it did, it would be a rational number. And we know from week 1 or week 2, whatever, root 2 is not a rational number. Well, if I were to truncate the decimal expansion here at the first decimal, second decimal, whatever, well, this would be a rational approximation. But if you think about it, any two truncations are going to be, so they're going to be of different orders of magnitude. And in fact, the distance between them is going to be some power of 10 to the minus whatever. 10 to the minus 1. Which means that this truncated sequence of rationals is a Cauchy sequence in rationals. But it does not converge to any rational number. And therefore, rationals is not complete. Make sense? OK. I'm not going to keep writing the rest. Here's another example. Compact intervals, or compact subsets more generally speaking, are complete. But if I were to look at a half-open interval, for instance, that would not be complete. Why? Because 1 over n is a sequence here. It is Cauchy, but it converges to 0, which is not in the space. OK? N centa 1 over n is Cauchy, but not convergent. So you need to think about convergence from the perspective of the space you're considering here. So from the perspective of this interval, there is no such thing as the number 0. It is missing. It's just a hole. That's why I call it incomplete. Any comments or questions about this?
I have two.
Yes.
First one, in the theorem B,
Yes.
number 2,
Yes.
right, you have a set S,
Yes.
right? It is, you call it complete relative to C0 matrix.
I'm calling the set of bounded functions from S to Y complete.
All right. Why in this 3 and you switch to an X?
Oh, in terms of notation? Just to distinguish that here, I don't need to assume that S is a metric space. Here, I do need to assume that X is a metric space.
Oh,
Yes. Because without assuming that X is a metric space, I cannot talk about what it means for a function to be continuous. I can still talk about boundedness, but I cannot talk about continuity. Because for any epsilon, there has to be a delta whatever. Right? So
S doesn't have to be continuous?
S is some arbitrary set.
Oh,
Yes. In the second item, whenever you have a set, you can talk about the set of functions from S to Y, and you can ask, oh, this set, this function is bounded or not. Because a function from S to Y would be bounded if its image is a bounded subset of Y. That's the definition of what it means for a function to be bounded. So for boundedness, all you need is a notion of a metric in the output space. But for continuity, you need a metric both on the input and output, so that you can talk about epsilon and delta. Okay. Second question?
yes. So it is a distance between arbitrary 2 points within the sequence?
Yes,
Has to come close.
exactly.
But you didn't tell us how to pick those 2 points. Once you pick the point.
Sure, I mean, no, but for instance, we can look at it like this. So what are two terms here? One of them is going to be n, the other one is going to be n plus p. Okay? For large n, I want this distance to be small. So I'm looking at this. What is this? This is no, I don't need the absolute values here. So the distance between the nth term and the n plus pth term is this. Okay? The point is that I can bound this let me think. Ultimately, in order for this to be Cauchy, I need to bound this by something that doesn't depend on P. Okay? So for some large enough n, so I want this to happen for n large enough and P arbitrary. I think the way to do this is to, in fact, call this, say, A, and then solve for n whatever. It's not super clear that you can bound this by something. Yeah.
Couldn't you also bound it by the first part by 1 over n, say that it's less than 1 over n, and then 1 over n, you can pick an n large enough to be smaller than any epsilon, and so it's also bounded by epsilon.
Hang on a minute. Oh, because we're taking n to infinity. OK. I was trying to take n to 0. Sorry. Like things are blowing up here. We're taking n to infinity here. Well, this is like a quadratic and stuff like that, so everything is fine. Yeah, you can make this arbitrarily small for large enough.
For any n that is greater than another big N?
Yes, exactly. Yes, because you're going to choose an epsilon. Based on the epsilon, you're going to need some capital N such that after it, this is bounded by epsilon. Yeah. Yeah, as n goes to infinity, these all go to 0, so things are fine. Another thing, of course, is that convergence is a relative notion. It depends on which space you're thinking of convergence in. But Cauchy property is not relative. I guess we're out of time. I ended up not proving anything. But I think it's much better that we have some understanding as to what this means. So ultimately, we're able to use this freely. OK, thank you. I'll see you tomorrow. There's an attendance sheet around, by the way.
All right, let's start. Good morning. Today we're going to keep working on infinite series. I wanted to say we're caught up on problem sets 8 and 9. We were behind in grading and writing down the solutions. So these are all good now. You should be able to see your grades on Canvas, on Gradescope. And I've written selected solutions for both of these. So the plan for the remaining classes, so we have 2 classes left this week, and then we're going to have 2 classes next week. Initially, I was planning to do a review next week, but instead of sort of separating the review parts from the main parts, I thought it would be better to slow down what we're discussing this week, like as I was doing before, and sort of kind of fold the review part into the discussion, because we're going to need certain things anyway. So for instance, with root test or ratio test, we're going to have to remember what limsup was. So I thought it would be good, and even what is inf and sup and all these things, I'll just take my time. So today I'm thinking of covering root test, ratio test, and m test, plus some epsilon, meaning some of the things that are minimal, that are sort of adjacent. On Friday, we're going to discuss formal power series, something called the radius of convergence, and this very important theorem, which is Cauchy-Adamar theorem, and some epsilon. And then Monday, I'm hoping to finally define real analytic functions, define formal derivatives and antiderivatives, and show at the very least real analytic implies C infinity. And then with the remaining time, we're going to do a review that is sort of more general. Now, first I want to start with an example. I had mentioned this, but I didn't actually compute. So if you look at the textbook, there's many more sort of tests. And indeed, there are other sort of textbooks that you can have a look. you know, there's a whole like industry of if this, that, the other thing, then the series converges, whatever. So I'm just picking and choosing the most interesting and the most thematic ones. One of them was, well, we looked at how the sum of the reciprocals of integers, that is to say zeta of 1, diverges. But I told you that if I were to multiply the terms by -1 in an alternating fashion, then that would converge. So I want to first discuss that. This guy is convergent. But the point, of course, is that it is not absolutely convergent. Remember, for absolute convergence, I need to look at the formal series made up of the absolute values of the terms. But of course, if I were to take the absolute value of this, I'm just going to get 1 over n. And that's zeta of 1, which we have discussed, diverges. So maybe I should say, so you can say this is conditionally convergent or, you know, not absolutely convergent. So let's say, but not absolutely so. Okay. Well, what does it mean for this to converge or diverge, whatever? You see, even though it looks more complicated, we've been discussing how formal series like this is nothing but a fancier or more complicated way of writing sequences, right? So this is all about the limit of the sequence of partial sums. So let me define S sub n to be the partial sum up to term n. By the way, you'll see this quite often, although not always, that when you're taking an infinite sum, the index is typically n. But when I switch over to finite sums, I switch over to k as the index. And I like to sort of reserve n as the sort of highest time that I'm adding to. This is like a convention. I just got used to not taking k to infinity, ultimately. I don't like taking k to infinity. But if you so desire, of course, these are all dummy variables. You can do whatever you want. So here's the idea. What is S1? S1 is just the first term, right? So that is -1. S2, maybe I should write it like this, actually. S2 is the sum of the first two terms. So I need to start with the previous one, and I need to add to the previous sum the nth term, in this case the second term. This is just 1/2. Okay, so whatever this number is. Let's not compute. S3, again, is going to be this plus the third term. The third term is -1/3, and so on. I'll write one more. Okay, it goes like this. Let's try to plot what's happening here. Say this is 0. I want to look at where these partial sums end up at. First, you go to -1. So there's this part, and then there's this part. In other words, they're the terms, the partial sums of odd index with odd index or partial sums with even index. So S1 goes from here to there. But then from S1 to S2, I'm adding something to it, but something not as large as where I've moved before. Right? So I moved at the end of time 1 step to the left, that's -1. And at time 2, I'm moving 1/2 step to the right. Okay. So it's going to go here, of course, but that doesn't really matter where it goes to. And if I'm transitioning from S2 to S3, again, I'm going to move to the left but not as far as where I've been before. Okay, then I'm going to keep going like this. So this thing sort of spirals to a certain point. Okay. Now, based on this, it seems like these partial sums should spiral to some number between 0 and 1. Consequently, it should converge. That's the heuristic. This is indeed correct, but now let's try to think about how to formalize this idea. How can I justify in a more rigorous fashion, based on this idea, that this has to converge? I'll give you a couple minutes. I want to use some ideas, right? Something about sequences of numbers ultimately. Even though these are sort of infinite sums or whatever, ultimately, at the end of the day, these are nothing but sequences of numbers. And I have only so many tools that I can use for convergence or divergence of sequences of numbers. I mean, this sequence is already bounded. Yeah, I guess you can do that, but there's a much simpler argument here. You could use Cauchy, but if you wanted to use Cauchy, you would need to calculate certain things, and you can certainly do that. But there's a much simpler argument here. What are the main results that we discussed all the way back in week 3 about sequences of numbers? There's Bolzano-Weierstrass, which, you could try using here, but even that is too much. We had discussed even more primitive tools compared to Bolzano-Weierstrass. That's too low of a level. I need a theorem. What is the other theorem about sequences? Think about it. Monotone convergence theorem. Right? So if you have a non-increasing or non-decreasing sequence of numbers, they have to converge to their sup or inf, whatever. The point here is that the odd-numbered terms and even-numbered terms are both monotone. It's just that the two things put together itself is not monotone. It alternates. But in any event, what you can say is that this specific subsequence, which correspond to these endpoints, is strictly increasing. 2 n plus 1, this subsequence is strictly increasing. And the partial sums with even number of terms is strictly decreasing. And indeed, we also have that any odd term is upper bounded by any even term. If you want at this stage, you can use the monotone convergence theorem, or what is equivalent, you can think about the nested interval property or nested interval theorem. You could just look at this interval, and then this interval, and then this interval, and so on, which by virtue of the fact that this is a nested sequence of closed and bounded intervals, and their lengths shrink to 0, well, that limit is going to be where this sequence converges to. By MCT, or nested interval property, converges. Okay. Pretty nice. Now, at this point, you might say to yourself, well, if we could just handle this using week 3 methods. Why didn't we discuss infinite series then? There's an incarnation of this class that does that. And if you look online and see other instructors teaching this course, there has been instances where people taught this course this way, even this specific course. I think we're just like sticking in this matter to Taylor's order. What it is that, this class, it is a bunch of like somewhat independent parts, and you can pretty much sort of discuss them in fairly independent order. The idea, I think, for Taylor's order is that ultimately this is going to escalate to analytic functions. So that's why we're sort of doing it this way. I wanted to say this also. Essentially using the same idea, you can generalize this statement to any sequence of the same form. That is to say, this is what is called the alternating series test. I'm going to leave that to you. The proof is pretty much this. You just write it out. Alternating series test. Let's write it like this. If you have a sequence of real numbers that converges to 0, then if you were to multiply these terms by -1 plus 1 in an alternating fashion like that, and add it up, that would converge. Not necessarily absolutely, but it would converge, at least conditionally. And like this. Because the point is that based on this, we have a similar thing happening here, and just goes through the exact arguments. Okay. Any comments or questions about this? Now, I want to transition to these important tests. One of them is the root test. The other one is the ratio test. Especially root test ends up being important in the context of analytic functions. Somehow, the root test is going to be closely related to the radius of convergence, and therefore Cauchy-Adamar. But and you've, in a sense, seen sort of instances of this, both the root test and the ratio test. Because remember, all the way back in week 3 or something, I gave you sequences, and then I asked you to figure out the limit of the sequence of roots or the sequence of ratios. That really sort of comes in handy here. And even though they look somewhat scary at first, these are all downstream from the comparison test. Okay? Ultimately, both the root test and the ratio test work because they allow you to compare whatever series you have to some geometric series. That's the main idea, really. Now, both of the statements for root and ratio test involve these limsup and liminf, which we haven't discussed in great detail throughout, because this is pretty much the only place that we use it in this course. So I'm going to write the statements, and then we're going to take our time and sort of unpack the definitions of these. And just so that I don't mess it up, I'll write it like this as well. So root test. Sometimes you might also hear the word radical test, because especially in older context or older literature or in algebraic literature, instead of the root of a number, you call it a radical of a number. Well, radical is just, so radix is just a Latin word for root anyway. So, okay. I'm going to take, let me see. Yeah, I'm going to take a sequence of real numbers. You've probably seen these before in Calc 2, whatever, in terms of the limits of the roots of these. But in general, requiring that the limits actually exist is too much to ask. And therefore, we're going to state these for in terms of limsup and liminf. Says this. Has 3 parts, or maybe 2 parts. If the limsup of the root sequence is less than 1, then the associated series is convergent. And in fact, it is absolutely convergent. Limsup as n goes to infinity of this is less than 1. And this is convergent. Okay. Now, as I'm writing this, if you don't remember what this limsup is, just pretend that it is limits. Okay? When the limit exists, limsup has to agree with limits. Another thing you should remember, you should know at this stage, even though you don't remember what this limsup is, no matter what the sequence is, this always converges to something. Maybe an extended number, but it always converges. We're going to unpack what this means in a second, but for now, I'm just I'm just giving you some heuristic. If, on the other hand, the limsup of the same root sequence is greater than 1, then the series is divergent. Yeah, even the original sequence is divergent. Okay. Now this is the root test. Ratio test is very similar. I'm going to start with some sequence that is to be added. And then I'm going to look at the sequence of consecutive ratios. Okay. Again, let x bullet be a sequence. Then, this time, instead of using limsup for both cases, one of them is liminf. Exactly. And presumably, in this case, I don't want these to be zeros. I want these to be defined. So let's say x bullet is taking values in non-zero reals, so that this makes sense. For any x, for any n, x sub n is non-zero. Looking at this, if this is less than 1, then again, absolute convergence. If, on the other hand, the liminf of the same sequence is greater than 1, then it is divergent. The original sequence already is divergent. It's divergent. And again, limsup is something similar to liminf. It always exists. And if the limit actually exists, it is equal to the limit. But it is something that is more broadly defined. Okay. How many of you have seen something like this before? In Calc 2, perhaps? Yeah, many of you have seen. Well, probably you haven't seen limsup and liminf. And you could, I hope at this point, appreciate why. Because in order to define even limsup or liminf properly, you would need to even, at the very least, make sense of supremum and infimum. And that's how we started this course. And that's why you haven't seen it in this generality properly, but this is the sort of more standard statement. And probably you also remember, or maybe some of you do remember, if limsup is 1 or liminf is 1, neither of these tests are conclusive. So let's try to write down an example. So, remark. Both of these tests are inconclusive for if you have equality with one. So you need to somehow separate these limsups and liminfs from 1 by some epsilon at least. Both of these tests are inconclusive in the remaining cases, let me say. That is to say, if somehow you get to show by some approximation, whatever, that the limsup here, whatever, this limit, is less than or equal to 1, but you cannot get like strict inequality, then you don't get to use this. It can go either way. And here's a standard example. Just look at zeta. Okay, zeta of S. I can think of it as a formal series. Okay, we know that this converges if and only if S is greater than 1, and diverges otherwise. But for instance, if I were to look at the, so here, x sub n is n to the minus s. That is to say, 1 over n to the s. Okay, therefore, this is this. Okay. Presumably, in a previous problem set, you did compute that n to the 1 over n converges to 1. So no matter what this s is, this always converges to 1. Okay. So in this case, the sequence of roots does converge. It always converges to 1, but for some s's, this is convergent. For some others, it is divergent. Therefore, the ratio, the root test is inconclusive. Okay. And likewise, if I were to look at the ratios, like this, what is this? This is n plus 1 divided by n raised to the power minus n. And again, as n goes to infinity, this approaches 1. No matter what the power s is, the limit is the same. Therefore, again, the ratio test is inconclusive if you don't get to separate these limits from 1. Okay? If things approach to 1, then things can go either way. Okay? Any comments or questions so far? Okay. Now, I'll say right from the get-go that root test is going to imply ratio test after some inequalities, okay? Because somehow the limsup and liminf of the root sequence sort of dominates the appropriate thing for the ratio sequence. Okay, we'll talk about that. But even before that, let's try to remember what this limsup is. Whatever limsup is, liminf should be the other way around ultimately. Okay, so if you can figure out one of these, the other one should follow. And so that's what I meant by folding the review into the topics. Recap. I'll say this too. In the literature, you might also see the notation lim with an over bar for limsup and lim with an under bar for liminf. So this is also written as this, and this is written as this for brevity. Now let's try to remember limsup. Any guesses, or do any of you remember what this limsup is? How I can start unpacking it? It's been a long time. I kind of mentioned the definition. Well, limsup supposedly should be the limit of suprema. Okay? So limsup should be the limit of sups. So limit of suprema. And so say this. This is going to be the limit of suprema. Okay. Because if this weren't the case, I mean, in general, this is not, of course, this sometimes doesn't work. But in this case, this notation sort of can be factorized this way. So somehow I want to write something like this. But then, whatever I write here should depend on n so that this actually makes sense. How can I put something here that would depend on n? Right, so I'm going to somehow come up with something that should depend on n so that if I take the limit of this, it always makes sense somehow. Think about it a little bit. I'm sort of doing this because it's going to take a while to remember these kind of things, and I want you to develop some sort of literacy about this. Of course, it's always possible to look back at the definition, whatever, but at some point, you want to develop some sense of sort of heuristics as to what things should mean without actually checking the literature. Well, what if I were to do this? Now, what does this mean? Let's again unpack. Well, initially, I had some sequence taking real values. Okay? But out of this, I can come up with a sequence of subsets of reals. These are just the tails of X bullet. Right, so for each n, I'm going to associate one subset of the reals. Zeroth tail is going to be all the positions that this sequence visits after time 0. First tail is going to be all the positions that the original sequence visits after time 1, and so on. Okay? Makes sense? Now, in principle, these could be like the same sets if your original sequence was like periodic or it was fixed, it was hitting the same points. But if it keeps moving around, as you increase n, what you're doing is, oh, I'm just going to look at my sequence, I'm going to look at its future, and as I increase n, I'm going to keep forgetting what happened at time 0, time 1, whatever. I'm slowly erasing the past. I'm just keeping the future. Okay? This is the nth tail. Make sense so far? Well, we talked about how any subset of the reals has a supremum. Any non-empty subset of the reals has a supremum that is possibly infinity. But in any event, for each n, that's a subset, which means I can look at its supremum. Okay? This is some possibly extended real number. It cannot be negative infinity because this set is non-empty. But it always exists. Ultimately, this expression, whose limit I'm taking, is an abbreviation for this. It's the same thing. And now, you see, this sup of the nth tail of the original sequence itself is a sequence of extended numbers. Make sense? And furthermore, I am guaranteed that the limit of the sups of the tails, this, is always going to, so it always exists. And here's why. Right, so this is zeroth tail, starts at x1, then x2, x3, and so on. First tail now starts at time 1. So it has everything except time 0, where the sequence was at time 0. If I start at time 2, then I'm going to start at position x2, and so on. Okay? And so as I increase n, I keep always getting rid of possibly some of the terms, which means this is a subset of this is a subset of this, and so on. So these tails are nested. Possibly they are the same, but in general, they could decrease. Okay. Now, if I were to compare the sup of this guy and this guy, well, it must be the case that the sup of this is larger. Why? Because I'm basically looking at the max. This guy has possibly more terms than this, so I have more opportunities to max out. So the sup of this is going to be not less than the sup of this, which itself is going to be not less than the sup of this. Okay? So let's write it. Sup of this 0th tail cannot be less than the sup of the first tail, which itself cannot be less than the sup of the second tail, and so on. Consequently, see, each of these is an extended number, and I'm just telling you that the sequence of extended numbers whose limit I'm taking is non-increasing. In other words, it is monotone. Therefore, by the monotone convergence theorem, this limit has to exist as an extended number. And in fact, it is also equal to the inf. And this should be m. By MCT. Okay. Make sense? So you can think of this limsup either as this or as this, depending on the context. The proof of the root test, and ultimately also the ratio test, is going to be all about basically opening this up. When we're doing the proof, I'm going to remind you this inf and sup as well. But basically, inf is sort of like a minimum, and sup is sort of like a maximum. Okay? So this is limsup. Liminf is the same idea, except that it's the other way around. It's the limit of the infima. And again, since the tails are decreasing, infima are non-decreasing. Again, they are monotone. And therefore, the limit has to exist and has to equal to sup. So, okay, by the same reasoning. Any comments or questions? Just by opening up the definition, you get to see that a sequence converges if and only if liminf equals limsup, in which case the common number is the limit. This was like an exercise that I gave back in the day. We're not going to use it here, so I'm just going to set it aside. I'll say one thing, though. When you think about what is happening here, how I define limsup and liminf, really the reason why this works is because my sequence is taking real values. Instead of a sequence, I could have looked at the nets. For instance, if I were to look at the net that defines Riemann integration, I can talk about limsup over sampled partitions, and limsup would give you the upper integral. Okay, I'll write that too. Say Riemann integrable on I. Say I is 0, 1 for simplicity. Limsup, as you might write this, PS goes to infinity, infinite in the resolution of the Riemann sum, is the upper Riemann integral, sorry, of the function. And similarly for the liminf. Okay, and how would you define this limsup in this case? Oh, I'll just write this part. Oh, okay. Again, I'm going to do minimax or maximin. Again, this should be the limit of suprema, limit over deltas. So these are going to be the mesh bound, and a sup over sample partitions that are whose meshes are bounded by delta. So I can just write it like this. Limit as delta goes to 0 in this case, because I need to take the delta to 0, and then sup over all sample partitions of the interval with the property that the mesh of the partition is bounded by delta. It's literally the same thing. Okay? Instead of looking at the tails parameterized by integers, you look at tails parameterized by, in this case, delta. Because I need to take it to infinity ultimately. You know, I need to take it to the future. Here, taking things to the future is about bounding from below the time. Here, taking things to the future is bounding the resolution or the size of the pixels. You can do the same thing with gauges too. You can talk about upper and lower HK integrals also. Pretty much the same way. Okay. The exercise is to sort of understand that this is true and do the same thing with liminf and whatever. Okay. Any comments or questions about either one of these? This is not super important. Liminf and limsup is important for what is to come. We need to do this minimax here for limsup and maximin here for liminf. And this is often the case. It's like if you're trying to get something, you often do like minimax or maximin throughout. Yeah.
In terms of Riemann integral,
Yes.
it is a limit, right?
Yes.
When the partition gets very small.
Yes.
And that is the inf of sup.
You can do inf too, yeah. Doesn't matter. Pretty much by the same reasoning, ultimately. It's just that it looks different, is the point. Yeah. Any other comments or questions? I have a couple minutes. Let's start the proof of the root test. All I need to do is, well, let me say it this way, okay? Here's the main idea. Let's call this limsup, it always exists as a number, as an extended number. Let's call it alpha. Okay. Okay. Say we're looking at the first case. In the first case, I'll draw it here. Here's 0, here's 1. In the first case, alpha is somewhere here. It doesn't really matter what it is, actually. All it matters is that it's between 0 and 1. And since I'm taking the limsup of non-negative terms, alpha is going to be lower bounded by 0 also. point is this though. Since this limit or limsup value is between 0 and 1, well, I'm going to be able to find some epsilon such that 1 minus epsilon is here for some epsilon. And 1 minus epsilon is going to be some number less than 1. Then I need to unpack this limsup whatever and show that the original sequence here is big O of 1 minus epsilon raised to the n. So xn is big O of 1 minus epsilon raised to the power n as n goes to infinity. This we need to argue, but once we have that, since we know that the infinite sum with these as the terms do converge by the geometric series, whatever, this has to converge also. That's what we're going to do. Okay. And similarly, in much the same way, in the second part, this time we're given that this limsup, this alpha value, is greater than 1. And again, I'm going to be able to find some epsilon such that 1 plus epsilon is less than alpha, but greater than 1. If I were to add the powers of this has to diverge. Again, by the comparison test. So we're going to show this. Again, we need to unpack the definition of limsup here. But since the sums of these terms blow up to infinity, I'm adding things that don't decay to 0. Right? Remember, so by the term test, if a series converges, the terms I'm adding has to go to 0, but this certainly doesn't. If this doesn't converge, by the comparison test, that means that the series with xn also cannot converge. That's what we're going to do. What we need to argue is, well, how do you get from the statement that alpha is the limsup that this happens, and likewise this? That's all we need to argue for the root test. For the ratio test, again, it's just a matter of opening up the definition of the limsup and rearranging things so as to get the same expression for these things. Okay? That's how we're going to prove these two things. Okay, I'm out of time. Thank you. We're going to continue on Friday. All right, let's start. Good morning. Today we're going to keep working on these tests that we started talking about last time. That tells you under certain circumstances, certain series converge. Once we're done with these, and in the meantime, we're also doing some sort of a review. Last time we had opened up this limsup expression. I want to go ahead one step further and deconstruct ultimately and go back to the assembly code of sup and inf as well in this context, turn them into epsilon delta type statements. So we're going to do that. We're going to look into proofs of these, and then we're going to transition to series of functions, which ultimately is what we're going to need for analytic functions. There's a very important test in the context of formal series of functions. This is what is called the Weierstrass M test. I want to discuss it. It's not very significant. It's not very sophisticated, its proof, but it's very important. It's very useful. So root test and ratio test. In the case of the root test, I start with a formal series of real numbers. Okay, and it says this: if the limsup of the sequence of the roots of the terms that I'm adding up is less than 1, then the series with absolute values of the terms converges, and consequently, by the comparison test, if you want, the original series converges as well. So this is, instead of writing it this way, people would just say this series, the original series, converges absolutely. That means you can just replace the terms that you're adding with their absolute values, and even that converges. So converges absolutely. On the other hand, if the limsup of the root sequence is greater than 1, then the sequence diverges. And again, by the comparison test, if this diverges, this has to diverge also. Okay. Okay, that's the root test. Ratio test, again, starts with a formal series of numbers. This time, I'm going to need that the terms that I'm adding are eventually non-zero, which means, if you were to guess, that means after finite time, so for large enough, all x sub n's should be non-zero. Maybe the first like 5 billion of them are 0 or whatever. But technically that's what this means. Why am I requiring this? So that I can look at these ratios. Right? I don't want this to be undefined. And again, this time you're looking at the limsup. And instead of using the limsup on the other side, you're going to look at liminf. If the limsup of the ratio sequence is less than 1, then again, absolute convergence. Then this time I'm going to write it like that. This converges absolutely. Saying that this converges absolutely is the same thing as, it's the same conclusion as this. Okay, it's just a shorter way of writing this. This is the same thing. And if, on the other hand, the limsup of the series of the ratio sequence is greater than, liminf of the ratio sequence is greater than 1, then you have divergence. Again, it's the same conclusion as this. And we talked about how, if either one of these limsups or liminfs could be possibly 1, so if you cannot bound these limsups or liminfs farther away from 1, then you're on your own, essentially, because it can go either way based on the zeta function type stuff. For NES, zeta of S satisfies that the limsup and liminf of the ratios are always 1, so that's an issue. Okay. Now, the proof of all of these ultimately are based on writing this out. Okay? So that's what we're going to do. I'm going to go ahead and start writing it down, and then once we have an idea, I'm going to record that expression in terms of epsilons, whatever, in the board over there. So let's start with the proof of the root test. So let's call alpha to be this limsup. And forget about either one of these assumptions, OK? I have a sequence of real numbers. I can go ahead and look at this limsup, which always exists as an extended real number. OK? So I'm just calling alpha, just notating it like that. It could be positive infinity. It's never going to be negative infinity. What I want to do is I want to go ahead and unpack this so that I'm not seeing any limbs and sups and nymphs, whatever. All I'm seeing is logical expressions and inequalities, ultimately. I want to go back to the assembly code. In this business, unfortunately, so throughout this course, we've seen sort of different situations where sometimes you don't need to open things up, whatever. In this case, you do. It's like with these kind of things, it's like you do have to open them up, unfortunately, as far as I know. I don't know any easier way of seeing this. So what is this limsup? It is, we said, equal to the inf over all n of the sup over all m not less than n. Okay. And what was this about? Well, for each n, I was looking at the tail after time n of the original sequence. That's a sequence of subsets that are nested. For each such subset, I was looking at the sup since the
tails are nested in a natural manner, if I keep increasing the time, so if I keep looking at further and further times, further and further tails, it's gonna decrease, which means that the limit here is the same thing as the infimum. Now I want to open this up. What does it mean for me to say that alpha is the inf of this? Let's take our time and slowly try to unpack this. Any ideas? First, I want to get rid of this inf. I don't want to see this inf. It's going to get more complicated, the statements, because inf means something. Saying that alpha is the inf of whatever means something. But what does it mean when I say alpha is the inf of whatever? It's a lower bound, okay? So inf is pretty much like a minimum. It's slightly more complicated, but that's the first thing to think about. I'm saying, right, so this is a function of n. You can think of it as a function, as a set, whatever. But this says, first of all, that alpha is a lower bound for this for any n. Right? Inf is supposed to be a lower bound. Okay? So what I can write is this. For any non-negative n, alpha is less than or equal to the sup of this. That's a lower bound. But this is not enough, because inf is not just some random lower bound. It's sort of like special in a sense. So I need to say something about that too. I need to describe somehow that this specific alpha is a special lower bound. How can I sort of say that? How can I describe that? So I need to say and, maybe I should write it here. Okay, so the second idea is this, right? So this is the best lower bound. What does it mean for something to be the best lower bound? You can say it in two ways. We're saying, so here is some things. Okay, this is this right-hand side. The expression with the sup. So far we said alpha is somewhere here. Okay, but I want to say there is in fact no gap in between. That is to say, I cannot just take this clamp, remember from week 3 or something, and I cannot keep pushing this any further. If I were to push it any further, something has to happen. Now, there are two ways of describing this. Either you can say it the way your colleague suggested. You can say, if I were to look at any other bound, this would be a greater number. In my opinion, that is a little bit less usable. What I like using is the other way around. I say, if I were to, so alpha is supposed to be somewhere here. If I were to push alpha just a little bit, I'm going to start missing certain points here in the right-hand side. Okay? I find that a little bit more useful, so I'm going to write it like that. And how can I say this? If I push alpha just a little bit more to the right, well, for any epsilon, I want to say alpha plus epsilon is not an upper bound. That's what I want to say. And for any epsilon, right, I want to say, OK, so I pushed alpha all the way here. In order for this alpha plus epsilon to fail to be an upper bound for this, well, it has to happen. It has to be the case that there is something in between. Okay? So for any epsilon, there has to be some n that possibly depends on epsilon, such that this expression is less than alpha plus epsilon.
Make sense? Now, we had done this a long time ago, but it's like we kind of used these ideas throughout, but it takes a while to get accustomed to sup and inf. That's why I'm sort of taking my time here to do some sort of a review. And you see how quite naturally this stuff just shows up. Any comments or questions here? So calling alpha to be the limsup of this sequence is equivalent to these two logical statements. But I want to go ahead and deconstruct even further. I don't want to see these sups over here. Now I want to get rid of this sup and this sup. How can I get rid of this sup? Any guesses? I'll give you a couple minutes. I don't want to see any sups whatsoever. In the first statements, how can I take this logical statement and come up with a logical statement that doesn't use any sup, but possibly uses more quantifiers?
Say there's some beta that is greater than all xm's, greater than above the index n.
OK, so your colleague is suggesting, well, I can just go ahead and say this sup is supposed to be an upper bound for these things. You can do that, but maybe this is where sort of the experience comes into play a little bit. I don't want to complicate the inequalities any further, OK? So I think about this. In order, OK, for alpha to be less than or equal to this sup, maybe I can write it like this too. So think of it like this. This is the same thing as writing. So the first statement is the same thing as writing this. OK. Now, I don't want to sort of do something here. What I want to say is this. For this set of numbers, its sup is greater than or equal to alpha. Okay? The only way this can happen is if there is at least one m greater than n, such that x sub m is greater than or equal to alpha. So I can say for any n, there is an m greater than n, such that alpha is less than or equal to x sub m. I'll write it here, actually. We're abbreviating the notation a little bit here. For any n, there is an m after n such that this happens. This is equivalent to saying this. Okay? Does this make sense? You see, I'm trying to get some sort of a chain. It's like for any something, there's a something, blah, blah, blah. That's sort of like been the logical sort of format that we've gotten accustomed to. So I'm sort of trying to get something similar to this. And so because, another thing here too is that I can just go ahead here and realize this is allowing me to farm a subsequence that I know is going to be for sure lower bounded by alpha. For n equals 1, there's a term, blah, 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 right? So I'm sort of like thinking of that too. So this is equivalent to this part. On the other hand, you see the second part is slightly easier because it says for any epsilon, there is some n sub epsilon such that the sup of these terms is upper bounded by this. So this alpha plus epsilon is supposed to be an upper bound for these terms, which means that for any m after this, x sub m is less than alpha plus epsilon. Okay. Make sense? These two statements together is literally the same thing as saying that alpha is the limsup of x sub n as n goes to infinity. Okay? So I'm going to record this here. Limsup what was it? The first statement is that for any n, there is an m such that alpha is less than or equal to x sub m, and oh, maybe I should have used some other letters. Let's use other letters so that they look more familiar. For any capital N, there is a lowercase n after capital N such that this happens. And for any epsilon, there is a capital N such that for any lowercase n after uppercase n, x sub n is less than alpha plus epsilon. I just did a change of variables here from that statement to this statement, but maybe this is more familiar. Okay. So you see, this part is almost like the limit. It's just that I have the upper bound only. I don't have the lower bound. So in the limsup case, the lower bound kind of is somewhat more shady, as you see. Upper bound works pretty much the same way standard limits work, but the lower bound is kind of janky a little bit. And of course, liminf is pretty much the same. It's just that you have to change the inequalities a little bit. I'm going to leave that to you to explicitly write it out, but I think it's a very good exercise, nice sort of practice. To be able to deconstruct or go back to the assembly code and rewrite what it means for liminf of a sequence to be beta, whatever. Okay? Do the same with liminf. Okay. Any comments or questions about this so far? Okay. Now I'm going to erase this. Because what I need to do this for is not really the original sequence xn, but instead the root sequence. So now I need to look at this guy. Okay. Getting rid of this. Now I'm just going to use this formula. Maybe I can say this is the red star. Then by red star, we have two things. That's equivalent to calling alpha to be the limsup of the root sequence. So you see, I need to change x sub n here with x sub n in absolute value raised to the power 1 over n. And in fact, OK, so while we're at it, yeah, so let's do that too. Oh, OK, I'll do it step by step. For any n, there is a lowercase n after it, such that alpha is less than or equal to x sub n in absolute value raised to the power 1 over n. And for any epsilon, there is an n sub epsilon such that after this, x sub n raised to the power 1 over n is upper bounded by alpha plus epsilon. That's what I have by the red star. And then I'm going to try to simplify this a little bit.
what I can do is I can raise both of these to the power n so that I don't have the nth root, or 1 over nth root, or I guess nth root, and likewise here. And I can write it like this. For any n, there is an lowercase n such that alpha raised to the power n is less than or equal to x sub n in absolute value. This comes from this. And for any epsilon, there is a capital N that depends possibly on epsilon, such that after this, x sub n in absolute value is like so. Okay? If I assume 1, that is to say alpha is less than 1, so that this is the situation, well, certainly I can engineer some epsilon such that alpha plus epsilon is here. Okay? Say by the whatever, Archimedean principle, all these things. Then there's an epsilon such that alpha plus epsilon is less than 1. Okay? But really, when you think about it, this says that x sub n is big O of alpha plus epsilon raised to the power n. So maybe I should say epsilon 0. Since x sub n is big O of alpha plus epsilon 0 raised to the power n as n goes to infinity, this is literally the second part. Well, we're done with this part by the comparison test, because we know that this converges. This is a geometric series. Okay. If, on the other hand, alpha is greater than 1, then we're in this situation. And I know by this part that for any capital N, there is some lowercase n after it, such that x sub n exceeds alpha to the n. Well, if alpha is to the right of 1, then that means that x sub n cannot converge to 0. This does not converge to 0. Because if it did, I wouldn't be able to come up with a subsequence that is bounded away from 1. But then by the term test, I know that this means that the series has to diverge. Remember, because term test says if a series converges, then its terms has to go to 0. Okay? Any comments or questions about this? So you see, pretty much the only part of the proof that was somewhat technical was actually writing out this limsup expression. Then we plugged it into the comparison test, whatever. Okay? So that's the proof of the root test. For the ratio test, we're going to try to make this resemble to this. And again, it ultimately boils down to opening up the limsup for the ratios. Okay? Yeah.
here's a proof of the ratio test. This time I'm going to put beta to be the limsup of the ratio sequence. And again, this is possibly an extended number, but it's never negative infinity. Again, by opening it up using red star, what do I have? I have that for any capital N, there is a lowercase n such that the ratios are lower bounded by beta. And for any epsilon, there is an n such that after it, the ratio is upper bounded by beta plus epsilon. Okay. I just again use the red star. Now, somehow I want to turn this into something that resembles more the root expression here. This is slightly more tricky, but here's something we can do. Okay, just look at the second part. For any epsilon, say epsilon is fixed. There is some n sub epsilon as well that is also fixed. If I were to choose lowercase n to be equal to uppercase n sub epsilon, this holds, right? Because I can just choose it like this. I'm going to go ahead and do this slowly. If I were to plug in lowercase n equals this, what do I have? I have this. This is upper bounded by beta plus epsilon. Sometimes it's a good idea to sort of plug in certain expressions to sort of simplify and write it out even more explicitly. What I can do, for instance, here is that I can plug in lowercase n equals uppercase n sub epsilon plus 1. That should hold again. Okay, this again is upper bounded by this. Okay. But you see, here's the nice thing about this. If I were to multiply this and this, well, this and this would cancel out, and I would have the ratio of the n sub epsilon plus second term to the n sub epsilon term. And on the right-hand side, I would have beta plus epsilon raised to the power 2. Okay, by just multiplying this by this and this by this. Make sense? But then if this is the case, you can just go ahead and choose lowercase n to be capital N sub epsilon plus p for some p arbitrary positive. This is again nothing but a change of variables ultimately in this expression, but makes it slightly easier.
For p non-negative, I can go ahead and define lowercase p to be this. For any such n, then, again, the same expression would work, and I would have some sort of a telescoping thing, and I would get this. In other words, maybe let's make it slightly better. I can take this to the other side and write it like so. So you see we're very close to getting the root. If I could take the n sub epsilon plus pth root of this, I would be pretty much done. And in fact, I can do this, and just gives you this. Okay. Well, let me first write it like so. It's going to be slightly easier. To see what is happening. Okay, now I take the appropriate roots. So that here I'm just going to have beta plus epsilon plus some junk, okay? Or times some junk. Times this expression raised to the power this. Raised to the power minus capital N sub epsilon times this term. And like so. So for any epsilon, there is a capital N sub epsilon, such that for any p, non-negative, I have this estimate. Okay? So you see, if I were to fix epsilon, now N sub epsilon is fixed, but p is arbitrary. So I can take the limit, or limsup, over p. The point of doing this would be that once I fix an epsilon, N sub epsilon would be fixed. So this expression, whose power I'm taking, is fixed in p. This is constant in p. So if I were to take the limit of this, or more specifically limsup of this expression as p goes to infinity, well, this is just some constant raised to the power 1 over something that goes to infinity, which means this is just going to go to 1 as p goes to infinity, which means that in the limsup, I'm going to have that this is upper bounded by this. Okay, so from here, taking p to infinity, we have that the limsup as n goes to infinity, n is here dummy, so it doesn't matter what letter you use. This is upper bounded by beta plus epsilon times something that goes to 1, which I'm not going to write. Okay. The point here is that this expression is constant in p. But if this is the case, I have that for any epsilon, the limsup of the ratio sequence plus epsilon upper bounds this. Well, if I were to take the expression of this, if I were to take the inf of this expression as epsilon goes to 0, I have what I need. Which is this. So the limsup of the ratio sequence dominates the limsup of the root sequence. Well, if this is the case, I can just go ahead and look at this. If the limsup of the ratio sequence is less than 1 by our inequality, This implies this, which then implies this, which is the same consequence as this. Okay? Follows from this together with 1 of root. Okay? Now for the other side, you need to do pretty much a similar argument. I'm not going to go ahead and do that and leave that to you. The main idea is this, okay? So the exercise is that likewise, the liminf of the ratio sequence lower bounds the liminf of the root sequence. So exercise, finish the proof of ratio test using this. After you prove it, of course. I did this part only. This is almost by definition. The main thing is this. Okay? Any comments or questions about this? So you see, on the one hand, it's not very sophisticated. We're just writing down the definitions. But then it's like, you know, it's a chore. You have to write it out. You write it out a couple hundred times, and then it becomes like second nature. Which you may or you may not need. Yeah, when I was taking this course myself, I was like, once I realized all you need to do is to write things down, I was like, anyway. Comments or questions?
So can I phrase it this way? A proof is essentially a comparison test.
Well, I mean, yes, but the word essentially does a lot of work. Yes.
And then in comparison test, we will make up a Bn.
Ultimately, yes.
And the Bn in here is the ratio.
Well, you want to compare it to some geometric series, but ultimately, yes. Yeah, that's why I said, you know, the mother of all tests is a comparison test. That's what I said. There are like many other tests like this, but ultimately you're comparing it to something that you know converges for sure, or you know diverges for sure. Yeah. Yeah, if you want, you could have thought of the proof of part 2 and the root test as me comparing it to zeta of 0. Zeta of 0 is just 1 plus 1 plus 1 plus 1, which blows up to infinity. And so in the proof of part 2 for the root test, I was comparing it to that. And so if you have a series that is below the series you're looking at, and if it blows up, then your original sequence series blows up also. You can think of it that way too. Yeah. Any other comments or questions?
I guess I'm a little confused on how the limsup of the root test being less than the ratio test implies that the ratio test one less than 1 implies the series converges. So
If
I think it would be less than.
if this, I'm saying this. If this, then this is less than 1.
Oh, because we're talking about the original sequence.
Yes.
Okay.
Yes. Yes. Any other comments? Okay. Now I want to transition to functional series. Okay. And in fact, I want to start with a nice exercise. Or perhaps, yeah, maybe 2 nice exercises actually. Exercise 1. Well, I want to define something called local uniform convergence for sequences of functions. We had talked about local properties. And the exercise is going to be, in fact, for you to define this. And once you define it, showing that local uniform convergence, whatever that is equivalent to saying convergent on each compact subinterval. Be a sequence of real valued functions on a non-empty open interval, say I, and f infinity again be such a function, then f bullet converges locally uniformly to f infinity. If and on f, it converges uniformly on each compact subinterval. Locally uniformly if and on f the restriction sequence on some k, or on any k rather, converges to the restriction of the limit uniformly on each compact subinterval or subset. Subinterval. The more common phrase for this is uniform convergence or uniform convergence on compacta. Because the older phrase for compact subset or whatever is compactum, and so the plural is compacta. Uniform convergence on compacta. It also ends up being the same thing as what is called compact open topology, but let's not get into that. Part of this exercise is to define what it means for a sequence to converge locally uniformly, and then once you show that, once you define it, show that this is equivalent to this. Just so that we can appreciate the value of this definition, let's think about an example. So a long time ago, when we were first talking about uniform versus pointwise convergence, I gave a very similar example. Think about the monomials defined on the unit interval, I said. But this time, let's define them to be on the open interval. Before, I was just looking at the closed and bounded interval. Let me let I to be this. I'm not including 1, okay? And for each n, f sub n be defined like this. Take an x, send it to x to the n. This is one of the key examples that you really should remember. Okay? We had kind of talked about the same thing before I was including the endpoints. And we showed last time we talked about this, that this converges to the function that is constantly 0, point-wise, except that we had this issue at 1. So this time, I'm not including the endpoints, so I'm just going to define f sub infinity to be 0. So the endpoints this time are not included. Of course, I could have included this part, but never mind that. And what are my terms? Say we start at 1. This is f sub 1. Then f sub 2 is x to the 2. It's a parabola. Okay, f sub 3 is the cubic, and so on. Okay? Now remember, here there is no issue with anything. So I just gotten rid of the point that was the contentious point last time. I got rid of the x equals 1 point. It's not in my interval. This sequence of functions converges pointwise to f infinity. Okay? Why? What does that mean? If I were to fix any vertical slice, then I have a sequence of numbers that go down to 0. But this is not uniform convergence. Even if I got rid of this point, I still don't have uniform convergence. Why? What is the point? Well, on each slice, yes, I have pointwise convergence, but the rates of convergences for different points is different. Right? If I were to look at points arbitrarily close to 1, well, I'm going to need to wait more and more. So uniform convergence fails. Pointwise convergence is OK. But in fact, local uniform convergence is true also. So if I were to look at any compact subinterval here, and if I were to just look at the restrictions, I would have uniform convergence there. Okay? Then not uniformly, but f bullet converges to f infinity locally uniformly, and hence pointwise, actually. So you see this local uniform convergence is some notion in between these two that we're just looking into now. This is going to come in handy when we start talking about analytic functions next week. Of course, we're just going to mention just the beginnings of this theory, but I thought it would be good. OK, that's it for this week. Next week, we're going to continue with quasi-new material, but I'm going to focus on doing reviews like this. Thank you.